Welcome back to another lecture from organic chemistry. In this lecture, I'm going to go through a subject that we call it the enantiomeric excess. I want to show you how to calculate how much from each enantiomer you have. We are talking about enantiomers. Enantiomers are compounds that they have exactly the same chemical formula. Their spatial and technically structures or 3D structures are different. That means their magnetic fields are going to be different, okay? So keep this one in your mind. Their magnetic fields are going to be different. Why? Because in one of them, the substituent is on the right side, on the second molecule is on the left side. So that means the magnetic field for each molecule, it will be different than the second one. And if you expose them to a magnetic field, that magnetic field, external magnetic field, will fill the magnetic field of each of these molecules. So we are going to use specific magnetic field to differentiate these two compounds. And that magnetic field, it can be a chiral environment like your body, and your body is capable of differentiate R from S. For example, we have some sugar molecules that, for example, R is sweet, S not, or opposite. Or ibuprofen, one of them is like one version is pen technically killer, and the second one, it can be even toxic. So whenever you make those chemical compounds, those enantiomers, you need to purify it and separate those two enantiomers from each other before you give it to any person. Okay, but for now, we're going to say their physical and chemical properties are the same. Okay, when it comes to chemical properties, they will be different when you subject them to chiral environment or polarized light. And what's a polarized light? We have light. It has electrical field and magnetic field. And light, it goes like, sinus, wave up and down. But it can come to, and it can reach the sample in any direction. I'm saying in any direction. So what I'm going to use a filter. That filter is going to let me to separate the waves from the lights from each other. And in this case, as you see, there are some white lines. They are up and down. That means only light that is reaching up and down. It can up and down. It can actually pass that filter. Now, if I don't have anything inside, for example, this tube. Okay, wave straight, it will go up and down until it's reached the second filter. And the second filter, if the second filter is aligned up and down like the first one, then I can see light is coming to my eyes. But if I rotate that light, by, for example, if I rotate it by 90 degree, as you see here, the input light is going up and down. So this one is up and down, while until here is up and down, that's fine. But when it's reaching the second filter, because it's perpendicular to the first filter, it will shut down any wave that is coming to it. And technically, we're not going to see any light, and it will be completely dark, and no light is going to pass it. Now, what we're going to do, we're going to put a sample somewhere inside this area. So we're going to put the sample there. And that sample, it might, change technically. It might change in a direction of the light. But we don't know which side is going to rotate the light, okay? We don't know that part. So, and what we're going to do, this, like light, it can turn to left or, right or left. And what we're going to do, we're going to play with the second, technically filter. We will tune the second filter. We keep tuning it until we see light. When we see light, now we read the gauge. And like how much rotation we had from the starting point. We know this one was up and down, and this one we had to tune it until see light. Why? Because the sample that we had there changed the direction. And it can be clockwise or counterclockwise. It's going to be maybe plus 15 or minus 15, okay? And sample, the machine that we use for this purpose, there is a polarimeter, and the formula for it is going to be specific rotation is equal to alpha divided by C multiply L, and L is the length. And whenever we report the alpha, the specific rotation, we reported under specific temperature and wavelength. You need to report those. Why? Because temperature is going to affect. Okay, temperature is going to affect technically how much from S or R you have, or the rotation. Okay, and so lambda, we use the D line of sodium, and wavelength for it is 589 nanometer, and the temperature, and in this case, it says the temperature is at 20 degrees Celsius, and it says D, that means they use D line for that specific sample. Okay, now we have alpha. Alpha, it will be the observed rotation. And the unit for it is going to be degree, and C, it will be the wave, C, it will be the concentration, is going to be mass, and a gram divided by volume in milliliter. And how about L? L is going to be the length, it will be in decimeter, and that's going to be equal to 10 centimeter. Okay, so imagine you put a non-chiral sample there, and you send light to it, okay? And you're going to put your eyes here, and you will watch, the light that is reaching to you. So you have a sample, and light is coming in this direction, and you want to see whether there is a rotation with the light or not, okay? So when you put in, non-chiral sample there, there will be no change with the light. Light is coming up and down, and you will see it stay up and down to the end. Okay, so up and down to the end. And in that case, if you looked at it, you will see no change with direction of the light. You started up and down, and end point, again, you got it up and down. So we say the change with the direction of light is going to be 0. Okay, what's the alpha? We call it the observed rotation. There is no rotation there, and because there is no rotation, we say it's non-active. What does it mean? Optically, it's not active. It's not rotating the light to the right or left. Only enantiomers can turn the light to the right or left, or chiral compounds. Okay, let's put it this way: chiral compounds will rotate it to the left or right. It's not changing it, so I'm going to say non-chiral. But if it's chiral and you send light to it, you very soon you will see change with the direction of the light, and say it started from here, and I'm gonna see some rotation, and when I put my eyes somewhere there and looked at it, I will see this. I will see the starting point, for example, here. That's going to be the starting point, and the end point I see there. This is going to be the alpha. That's it. The observed one is anything other than 0. Alpha can be positive or negative. So alpha, it can be positive or negative. If it's a positive, we say it's turning the light to the right side, or clockwise. And negative, it will be counterclockwise. Okay. So let's practice some sample. In this case, some sample questions. In this case, we have mass, and it's equal to 20 gram. Volume, we have it equal to 100 milliliter, and the length, we have it equal to 4 decimeter. So have this length equal to 4 decimeter. So I'm going to say C will be equal to 20 gram mass divided by the volume, 100 milliliter. Okay, so you say 20 divided by 100. That's going to be 0.2, and the unit, it will be gram over milliliter. Okay, let's calculate the specific rotation. The specific rotation is going to be alpha, the observed one, divided by C multiply L. And what was the alpha? The observed one. Okay, the observed one, this is the, okay, where was it? This is the observed one. Okay, so the observed one, it says, is minus 20. So we go minus 20 divided by 0.2 gram over milliliter. Okay, multiply. You don't need really to write the unit here. Just put the number 0.2, multiply 4 decimeter, and calculate that one. So I go 20 divided by 0.2 divided by 4. I got this one equal to 25 degree. It's negative, so I'm going to say the specific rotation is minus 20. What does it mean? Okay, for okay, alpha, okay, for pure sample, okay, pure sample, rotation, it will be minus 25, okay, for pure sample, if it's a pure sample. So how come the observe, okay, is minus 4, okay, minus 4. It means inside the solution, okay, the solution has R and S enantiomers, or you're dealing with mixture. Okay, and because you have mixture, and some of the second enantiomer will cancel the one that we have excess from it. It will cancel some of them, and it will drop the rotation. And it will bring the rotation to only -4 instead of -25. Okay, so we got here, and now when it comes to rotation, R will have exactly opposite of S, S rotation. The rotation will be exactly the same, but the only difference between them, it will be the sign. Okay, but the numbers will be the same. So R and S will have opposite, configuration. Opposite rotation. Okay, and plus is talking about the direction, in which direction we are turning to light. Is it to the right side or left? Okay, there is no, okay, listen carefully, there is no connection between R and minus or R and plus. And also, there is no connection between S and minus or plus. Okay, we don't have such a connection. R, it can be plus or minus. S, it can be plus or minus. Don't connect them, okay? Don't say because R is negative here, so R forever is going to be negative. That's not true, okay? R can have any direction, okay? And here, sometimes you will see these two terms, that dextro rotatory and levo rotatory, and you can go with dextro. I know the pronunciation is going to be hard, dextro or levo. Dextro stand for rotation to the right side, and levo for rotation to the left side. And now, if you change the temperature, you will see difference, like in direction of the rotation. So always you have to report, that's a specific observation, a specific, the observed rotation. You have to specify it, with writing actually the temperature, in which temperature you measured. That's actual rotation. Okay. Now, what will happen if I have exactly the same amount from R and S? In that case, we say you are dealing with a racemic mixture. What does it mean? It means it will be non-active, or optically not active. Yes, you do have R and S configuration, but because they have exactly same rotation, they will cancel each other. So alpha will be equal to 0. It doesn't mean you don't have optical compound there. You do, but they are exactly the same and they cancel each other. If we go back, if we take 50% from this and add it here, let's say, okay, mix this two, 50-50%, and from R and S, one is turning it to minus 23 degrees. So let's start from here. If this one is 0, it will turn it to minus 23.1. Now, when you add the S, it will bring this one back and it will put it here. And again, the alpha is going to turn to 0 because they will cancel each other. Now, if you have excess from one of those enantiomer, then you will see some rotation. Okay, you will see some rotation, and there is a way to calculate how much from that specific enantiomer we have. Okay, so we're going to read the observe, rotation. Okay, that one is going to be easy to read it. And how about the pure one? Where do I get the pure one? So let's say you made a compound, and there are plenty techniques in chemistry that you can use to say whether this compound is pure or not. Okay, so now that you figure this compound is 100% is pure, you put it inside the polarimeter and you will measure the rotation. That rotation, it will be specific rotation of that enantiomer. And you know that an enantiomer is 100% pure. How? You use other techniques to confirm whether it's pure or not. Okay. And if you divide those two and multiply it by 100, that's going to give you the percentage of the enantiomeric excess. And I believe we have a good number of questions. Okay. I'm going to practice some question for you guys, and I will show you how to, how to calculate an enantiomeric excess from for each actually enantiomer. Okay. So if we are dealing with a racemic mixture, because we have R and S, we have 50-50% from each, they will cancel each other, and alpha, the observed one, it will be 0. But in the second one, we have 70% from R and 30% from S. What do I see? What I'm gonna be able to see? Okay, remember this. You have 70% from R and 30% from S. So the 70% from R, I'm going to write it this way. I'm going to say we have 40% from R plus 30% again from R. Okay. And then we have 30% from S. These two, they have opposite rotation. Okay. The rotation here is negative, while the S, the rotation is positive. 30% from R, it will be canceled by 30% from S. So the rotation for 30 plus 30 is going to be exactly equal to 0. When you see, like rotation, the rotation is going to be because of this. You have 40%, and that's going to give you rotation anything other than 0. And the observed, it will be because of the 40%. What did I write? Observed. Okay. The observed alpha is going to be because of the 40%. Okay, I'm going to stop the lecture here. In the next lecture, I will practice the 3 methods to calculate the enantiomeric excess for you. And I will see you very soon. Thank you.